Welcome to NPTEL MOOCs course on Machine Learning and Deep Learning, Fundamentals and Applications. In my last class, I discussed the concept of Bayesian decision theory. I explained how to determine the decision surfaces between the classes. So, during that discussion, I considered that the class conditional density follows a Gaussian distribution. And based on this, I have determined the location of the decision boundary. The decision boundary is orthogonal to the weight vector if I consider the diagonal covariance matrix. The covariance matrix is same for all the classes and I am considering the diagonal covariance matrix. For this case, the decision boundary will be passing through the point x naught and it is orthogonal to the weight vector. The weight vector is nothing but the difference between these two means, one is mu I and another one is mu j. So, that concept I have explained in my last class. The second case is if the covariance matrix is not diagonal, non-diagonal, then what will be the location of the decision boundary? So, that concept I am going to explain today. So, let me start this class. So, how to find the decision boundary between the classes? The condition is the non-diagonal covariance matrix. So, this is a Bayesian decision theory, how to determine the decision surfaces. So, in my last class, I have shown that discriminant function gix, it is in the form, the weight vector is there, wi is the weight vector and x is the feature vector and I have the bias or threshold. So, this is the weight vector. And this is the bias. So, this weight vector, it is nothing but the inverse of the covariance matrix and the mean of the class omega I, and this bias is ln So, we have determined this. If you see my last class, you can see this derivation, and for this what we have considered, mu I dot xt is equal to x dot mu I transpose. So, this we have considered. So, this is the expression for the discriminant function, and after this what I considered, the case number 1 is that diagonal covariance matrix. The covariance matrix is same for all the classes and is the diagonal covariance matrix. So, corresponding to this, the weight vector we have derived, the weight vector is nothing but the mean of these two classes. We have considered two classes, the class is omega I and another class is omega j. Two classes we have considered, and also we have considered x naught. X naught is the point we can determine like this. This is mu I plus mu j minus sigma square So, we have determined x naught like this. So, in my last class also I have shown how to draw the decision boundary. So, suppose this is the feature space. So, suppose it is x1 and x2, two-dimensional feature space. Now, corresponding to the first class, this is the mean vector, and corresponding to the second class, and this is the mean vector mu j. After this, I have to determine the difference between these two means. So that is nothing but, this is the vector, this vector is mu I minus mu j, and that is nothing but the weight vector, that is nothing but the weight vector. And after this, I considered the point x naught. So this is suppose x naught. Now how to draw the decision boundary? The decision boundary I have to draw, that should be orthogonal to the weight vector. So you can see this is orthogonal to the weight vector, and it should pass through the point is x naught. So this is the decision boundary. So decision boundary, how to determine? So decision boundary is orthogonal to the weight vector. The weight vector is nothing but the difference between two means mu I and mu j, and also the decision boundary will pass through the point is x naught. So this is true for this case. The case is we have the diagonal covariance matrix, and covariance matrix is same for all the classes. So corresponding to this case, we have this decision boundary. Now let us go to the case number 2. So in the case number 2, we are considering non-diagonal covariance matrix. Non-diagonal covariance matrix. So that means in this case we are considering the covariance matrix is same for all the classes. So it is same for all the classes, but it is not diagonal. In case number 1, we considered that covariance matrix is a diagonal matrix, but in this case we are considering a non-diagonal covariance matrix. So corresponding to this case, decision surface will be Gij x is equal to W transpose x minus x naught is equal to 0. So what is the weight vector? The weight vector in this case, you can get the inverse of the covariance matrix, mu I minus mu j. And what is x naught? X naught is equal to 1 by 2 mu I plus mu j minus ln is probability of omega I divided by probability of omega j, and mu I minus mu j mu I minus mu j whole square, and it is the inverse of the covariance matrix. So these will be the expression for the weight vector and the vector x naught. Now in this case, the decision boundary, or I can say the decision hyperplane, decision boundary or hyperplane is no longer orthogonal to the vector mu I minus mu j. So you can see in this case that for the non-diagonal covariance matrix, the decision hyperplane is no longer orthogonal to the weight vector. That is actually the weight vector. So decision boundary will pass through the point is x naught. So x naught already we have defined, but one difference between the previous case, the case number 1, that decision hyperplane is no longer orthogonal to the vector mu I minus mu j. So this is for the case number 2. Now let us consider the classifier. That classifier is called minimum distance classifier, and based on this concept, the concept is nothing but the discriminant function. So how to develop the theory for the minimum distance classifier? So let us discuss about the minimum distance classifier in the next slide. So what is the minimum distance classifier? Minimum distance classifier minimum distance classifiers. So, we consider equiprobable classes we are considering with same covariance matrix. So, in this case 1, in equation number 1 what we have determined, if you remember, that is the expression is GIX, that is the expression for the discriminant function 1 by 2 x minus mu I transpose, and it is plus. So, we have this expression. So, you know this expression. In my last class I derived this expression. Now, we are considering equiprobable classes. So, corresponding to this case equiprobable classes with same covariance matrix, I can write this expression GIX is equal to simply 1 by 2 x minus mu I transpose, and this is a covariance matrix because covariance matrix is same for all the classes, x minus mu I. So, we are considering the equiprobable classes. So, this part is not so important. So, we are writing this expression. Now, the first case we are considering, this is the first case. Suppose the sigma, that is the covariance matrix, is a diagonal covariance matrix. If I consider the diagonal covariance matrix, diagonal covariance matrix we are considering. So, for a diagonal covariance matrix, because for a classification we have to see the maximum discriminant function. So, which one is maximum, that which one is the largest discriminant function out of C number of discriminant function we have to determine. So, this maximum GIX, the maximum discriminant function, means minimum Euclidean distance. From the respective mean points. So, this maximum discriminant function means minimum Euclidean distance from the respective mean points. So, what is the Euclidean distance? So, Euclidean distance I can write like this, dE, that is the Euclidean distance, is equal to, so here actually I am showing the Euclidean norm between x and mu I. So, this is the Euclidean distance. So, maximum discriminant function means the minimum Euclidean distance from the respective mean points. So, if I consider the constant, suppose constant dE, constant Euclidean distance, suppose we are considering, that means we will be getting the curves of circles. And if I consider the high dimensional case, then it will be hypersphere. If I consider the constant Euclidean distance, I will be getting the curves of circles, and if I consider the high dimensional case, then it is the hypersphere. So, this is the case number 1. So, now go to the case number 2. The case number 2, what is the case number 2? Non-diagonal covariance matrix is this. So that means we have to maximize the discriminant function, maximizing GIX is equivalent to minimizing the inverse of the covariance matrix, minimizing of this. So minimizing the discriminant function is equivalent to minimizing the inverse of the covariance matrix norm. So that is actually we have to minimize the Mahalanobis distance. So Mahalanobis distance you can write. So already I have defined. So it is x minus mu I transpose x minus mu I. This is 1 by 2. So now let us consider the constant Mahalanobis distance. The Mahalanobis distance dm is equal to c. So corresponding to this, I will be getting curves of ellipses, and if I consider the high dimensional, then I will be getting hyper ellipses. So for constant Mahalanobis distance, I will be getting the curves of ellipse, or maybe high dimensional, I will be getting hyper ellipsoids. So these two cases we are considering. So for maximizing the discriminant function, I have to consider minimum Euclidean distance, and also the same thing for maximizing the discriminant function GIX, I have to minimize the Mahalanobis distance. So in the first case we have considered the diagonal covariance matrix. In the second case we are considering non-diagonal covariance matrix. So these two cases I can show like this. So what is the meaning of this? So suppose I have two classes. So this is the centroid of the first class, that is the mean of the first class, and these are the contours. So I am considering some of the contours. So this is my mu 1, and I am considering another class. So another class, suppose this class. So this is mu 2, mu 1 and mu 2. So what is the weight vector? The weight vector is nothing but the difference between these two means. So this is the difference between these two means I am drawing. That is the weight vector. Now my decision boundary will be perpendicular or orthogonal to this vector. So this is my decision boundary. This is the decision boundary. So these are the contours. These are the contours of equal Euclidean distances. These are the contours of Euclidean distances. So you can see this is the bisector we are considering, and bisector is the decision boundary. So this bisector is orthogonal to the weight vector. The weight vector is nothing but the difference between the two means, mu 1 minus mu 2. Okay. So these contours, if I consider in two dimensional, it will be circle, otherwise this may be hypersphere. Similarly, if I consider the Mahalanobis distance So suppose this is one class and we are considering some contours, and this is suppose mu1, and another class we are considering, another class is so this is my mu2. Now I have to determine the difference between these two means. So this is the difference between these two means. So in this case, because we are considering non-diagonal covariance matrix, the decision boundary will not be orthogonal to the weight vector. So maybe the decision boundary may be something like this. It is not orthogonal. This is the decision boundary. And this is not orthogonal. This is not orthogonal. So if you see, we are considering these are the contours. These contours, you can see these are the ellipses. In two-dimensional, these are the ellipses. So that means in this case we are considering equal Mahalanobis distance. These are the contours of equal Mahalanobis distance. So I can write the contours of equal Mahalanobis distance. So for two-dimensional, it is the contours of the ellipse, and if I consider the high dimensional, then we can consider hyperellipsoid. Hyperellipsoid. For high dimensional case, we can consider hyperellipsoid. So you can see the pictorial representation of one is the Euclidean distance, another one is the Mahalanobis distance. In the first case, we consider the diagonal covariance matrix, and corresponding to that case, you can see we have the orthogonal vector. That vector, that is the decision boundary, is orthogonal to the weight vector. In the second case, for the non-diagonal covariance matrix, the decision boundary is not orthogonal to the weight vector. So this is the concept of the minimum distance classifier. So let us consider one problem on this Mahalanobis distance and the Euclidean distance, and how you can do the classification by considering the minimum distance classifier. So let us move to the next slide. So suppose this example we are considering. Two classes we are considering, and same covariance matrix we are considering for these two classes. The covariance matrix is sigma. So it is 1.1, suppose 1.1, 0.3, 0.3, 1.9. This is the covariance matrix. And corresponding to the first class, the mean is mu1, and it is 0, 0, and this vector is 0, 0 transpose. Second mean is mu2, this value is 3, 3, and transpose we are considering. Now the problem is we have to classify vector. The vector is 1.0 and 2.2 transpose. So first let us consider the Mahalanobis distance. Mahalanobis distance between the first mean and the Fisher vector. The Fisher vector is suppose x. So corresponding to this, you can see Mahalanobis distance is, this is the expression for the Mahalanobis distance. So it is nothing but 1.0, 2.2, this will be 0.95 minus 0.15. So you can check these calculations, 0.55 and it is 1.0 and 2.2. So, corresponding to this value will be 2.952. So, this is the squared Mahalanobis distance is like this. So, this is the distance between mu1 and x, and similarly we can determine the Mahalanobis distance between mu2 and x. That also you can determine. This is minus 2.0 minus 0.8, this is 0.95 minus 1.5 minus 1.5 0.55. So, it is minus 2.0 and minus 0.8. So, corresponding to this distance is 3.672. So, you can see these two distances we have calculated, and based on this input Fisher vector is assigned to the class with the mean vector 0 0, because corresponding to this mean vector I have the minimum distance. So, I can write the vector x is assigned to the class with mean vector is 0 0 transpose. So, based on this Euclidean distance we can do the classification. This is the minimum distance classification. So, corresponding to the first mean, your minimum distance is 2.952. Corresponding to the second mean, the distance is 3.672. So, then we have to consider the mean mu1, that is the 0 0. So, that the Fisher vector is assigned to the first class. But again, if I consider, suppose again given vector, the vector is the Fisher vector and vector is 1.0, 2.2 transpose is close to the second mean with respect to Euclidean distance. So, if I consider Euclidean distance, the result will be different. In case of the Euclidean distance, the Fisher vector x is assigned to the second class. But in this problem, we are considering the covariance matrix. So, that is why we have to consider the Mahalanobis distance. So, based on the Mahalanobis distance, we can determine the particular class. So, we can decide. So, that is the concept of the minimum distance classifier. So, this is the fundamental concept of the Bayesian decision theory. So, up till now we have discussed how to determine the particular decision boundary. So, in this class I discussed how to determine the location of the decision boundary. I considered two cases. In the first case, I considered a diagonal covariance matrix. The covariance matrix is same for all the classes, and corresponding to this I have determined the location of the decision boundary. The decision boundary is orthogonal to the weight vector. Weight vector is nothing but the difference between mu I and mu j, the difference between two means, and it should pass through the point is x naught. This is corresponding to the case 1. In the case number 2, we considered non-diagonal covariance matrix. In this case, the decision boundary is not orthogonal to the weight vector, but it passes through the point x naught. So, that is the difference between case 1 and case 2. After this, I discussed the concept of minimum distance classifier based on Euclidean distance and also the Mahalanobis distance. So, these concepts are quite important: the concept of the minimum distance classifier, the concept of the Bayesian decision theory, and how to determine the decision boundary corresponding to the normal distribution. Normal distribution means we are considering that class conditional density follows normal distributions. So, let me stop here today. Thank you.